Shallow water remote sensing is what I should be talking about this morning. Whereby I mean where you can see the bottom in the imagery. That's what I mean by shallow water. Strictly speaking, you should call it optically shallow water, because of course you can have shallow water where you still can't see the bottom. So I've got quite a range of topics to get through here. As you can see, I may not quite get through all of them. I've got a sort of plan B. I might drop a couple of things towards the end. We'll see how far we get. I'll give a brief overview. I'll talk about the kind of imagery we use for shallow water applications, which is generally high spatial resolution compared to what you use for ocean color. I'll talk a bit about empirical methods, machine learning, this type of methods. I'm going to talk a bit about sun-glint correction of high spatial resolution images, something that's been mentioned already a couple of times by David. Model inversion methods, canopy modeling, and then I'll get into uncertainty propagation and multi-image analysis. And then finally, if I've got time, I'll briefly mention ISAT-2, which is a space-borne LiDAR, which is very useful for shallow water applications. So let's start then. So in a shallow water situation where you can see the bottom, you've got three components, any of which might be of interest, which is the bottom reflectance, the optical properties of the water, and the bathymetry. If you're only interested in bottom mapping, the optical properties of the water that you don't know or might vary, and the bathymetry, which might also be variable, are confounding factors. They sort of get in the way of being able to get to the bottom reflectance, which is what you want. And similarly, if you're interested in any of the other two things, the other things are confounding factors to get to that. So the three things operate together. The kind of applications of interest are things like spatial ecology. So you want to be able to look at where coral reefs are, where seagrasses are over time. You can understand something about the science of the ecology of those environments. Resource mapping, marine protected area design. You need to be able to map where things are, understand what you've got spatially in your area. And linked to that is the ecosystem services. So a lot of shallow water environments provide ecosystem services that have a kind of commercial value, essentially. Like coral reefs act as for coastal protection, they protect against wave erosion. Seagrasses are an important blue carbon sink because a lot of seagrass species store all of carbon in their rhizomes, so they can be an important blue carbon sink like that. Tourism is important in many places. It relies on a nice coral reef. If the coral reefs die, the tourists don't want to go there anymore. All of this kind of stuff. There's a commercial, economical value to these things, so it's useful to be able to assess them by remote sensing. And then finally there I've got hydrography, by which I mean bathymetry, mapping bathymetry for the purposes of navigation principally. There are certain places in the world that have never been surveyed for bathymetry since the days of Captain Cook in 1770, whenever it was. And I'm talking about places like Pacific Islands, remote islands, and stuff like this, where it's very expensive to send a survey boat there. So they haven't done, and they don't want to. So if they can assess or map the bathymetry using satellite-derived bathymetry, that's of interest. So there's quite a bit of interest in satellite-derived bathymetry from hydrographic offices in various places around the world. In this talk, I'm going to mostly talk about bottom mapping and bathymetry, but I will mention optical properties a little bit, water optical properties. So this is mostly going to be sort of focused on if you want to do bottom mapping or bathymetry, but we'll touch on, the issues of determining water optical properties as well in these kind of shallow water environments. So this is a slide similar to what Wayne showed. Along the bottom here, we've got spatial resolution, and up here, temporal resolution, which is imagery acquisition, repeat time. So this is just to give an idea of what we would quite like to have in terms of imagery for doing these kind of activities. And the main point is, so this is a slide I pulled from a paper about Sentinel-2. So it's got Sentinel-2 as a box here, but actually we're really interested in this red area. So we've got things like benthic change detection, habitat mapping, bathymetry, geomorphological mapping, and down here bleaching detection. That's coral bleaching. So I guess you guys probably all know when corals are stressed, they turn white, and you can actually see that in satellite imagery. It's useful to be able to detect when corals are bleaching. So what kind of temporal and spatial scales we want? Well, we definitely want less than 100 meter scale pixels, ideally down to 10 meter pixels or even less. And temporarily, it depends on what you want to do. But in the bleaching, for example, which would be the best, it would be the hardest thing to do, really. You really want acquisitions more than once a day because of the period the bleaching occurs in, and because not every image is a good image. So you need quite a lot of images to be able to do this kind of stuff. But, you know, for benthic mapping and so on, you could get away with doing it once a year. So you just want several images a year would be good. So basically, the take-home message is we're talking about higher spatial resolution. That's really the key. What we really want, which is 1 meter resolution several times a day, we can't get it yet, but maybe one day we will. So just talking about the kinds of imagery we can use currently. So for pixel sizes less than 5 meters, we're mostly commercial operators, of which there have been many over the years and continue to be more and more. And the archives are still available of the previous providers. So you've got things like Pleiad, all the digital globe images, worldview images, worldview sensor, GeoEye, Iconus, and now you've got Planet, SuperDove, all this kind of stuff. Usually, well, typically they would have had 4 bands in the past. Now increasingly they have 8 bands. So it used to be you just get red, green, and blue and near infrared, but now you get a few extra bands. Then if you can go tolerate a slightly larger pixel size, say 10 to 30 meters, then you've got the space agency satellites like Landsat 8, 9, and Sentinel-2. Now, the key thing here is that the commercial satellites tend not to have as good radiometry as do the space agency. These commercial operators don't put in as much effort into, you know, calibration or assessing the degradation of the instrument over time, this kind of thing, as do ESA and NASA, you know. So you'll have better quality in terms of radiometry imagery with Sentinel-2 and Landsat than you will with the commercial operators. And also, you know, things like signal to noise ratio are a bit better because the pixels are slightly larger. So you've always kind of got this question of like, what's the optimal resolution to go for? You know, you might be able to go, oh, great, I can get 2 meter pixel size with one of these commercial type satellites, but maybe actually you'd be better off with 10 meter pixels with Sentinel-2. You just have to decide for your application what's the best. And another important point is for these kind of satellites, the bands are relatively spectrally wide compared to what you might be used to for your ocean color satellites. So this is an example of WorldView 3-band relative spectral response functions compared to MERIS and OLCI, which I've stretched these so they're kind of on top of each other, and you can see how wide the bands are for WorldView compared to these narrow bands you get with the ocean color satellites. And that's partly a physical constraint, because if you go to smaller pixels, you're looking in a smaller solid angle, so you get less photons. So you have to make the wavelength band wider in order to get enough photons to get to an acceptable signal to noise ratio. But the signal to noise ratio will not be as high still as your ocean color satellites with these kind of instruments. So an important point with this stuff is if you're doing modeling work like forward modeling or model inversion type approaches, you really want to be modeling, well, ideally from the best accuracy, you want to model hyperspectrally and then convolve your hyperspectral results to the relative response function of the instruments, because it's not very accurate necessarily to just treat them as a single wavelength band. You can't say, oh, this is a band at whatever 420 nanometers, because actually it's quite wide. And really you want to model a spectrum and then convolve it to that relative spectral response function for the most accuracy. I mean, again, it depends what you want to do. You might be able to get away with just treating them as single wavelengths or not. So here's an example of the kind of imagery that you get, and I can use it to illustrate a few points. So this is a WorldView 2 image of the Yucatan coast, Mexico. It's a coral reef lagoon area. So on the right here, you've got corals. This is a lagoon. This is seagrass, this stuff here, and then here's the land. And so over here, it's deep because it drops down deep very soon after the coral reef ends. So this is a kind of deep water area. So this is your more normal ocean color kind of area. You can't really see the bottom here, or if you can, pretty soon beyond there, you won't be able to. And then you see it gets shallower, and you see the spectral changes. It's getting shallower. This is sand. These bright patches of sand here. This is the spur and groove zone of the reef. So you see between the corals here, these little patches of sand, which you can make out quite easily in this image because the pixels are quite small. And then you come over here and then you've got various stuff in the lagoon. These are corals here. I can tell just by eye that they're corals just because I know what I'm looking at, sort of thing. And this is seagrass over here. If you look at the same scene in a Sentinel-2 image, this is 10 meter pixels. Now you see it's a bit different. So it's it's the same scene, still got deep water over here. But when you're coming in here, you can no longer distinguish the patches of sand from the corals. So the pixels in here are what we would call mixed pixels. Within the pixel, you've got different bottom types. And that's something that you need to think about if you do bottom mapping or any applications where you need to understand what the bottom reflectance is, which is basically anything, because the bottom reflectance is a contributor to the reflectance in the image. So it's a bit different. It kind of looks blurry, but you can see the basic things. Okay, so here's seagrass again, fairly clearly. So for mapping seagrass, this might be all right, but you're a bit tricky down here. If you want to distinguish between sand and corals, you probably can't do it very easily. But this would have better radiometry, this image. So if you wanted to do model inversion techniques and so on, you might be better off with this than with the other image, possibly. I mean, it's speculative, but that's the kind of thing to think about. So some of the methods that might be used. Okay, so I'll start by talking about empirical methods, and I've just got a few brief slides about this. And by an empirical method, I mean a method where you have data which you train maybe a classifier or a machine learning or a simple regression algorithm. So these are empirical methods for bathymetry, and these are the main two that you'll come across, or variants of these. And one is by Lysenga in 1978, and the other is various methods by Stumpf, which are, again, are around a similar concept. Basically, both of these rely on the idea that the attenuation of light with depth is exponential, which you've seen. It's like your KD, concept of KD. And they assume that KD and effectively KLU is constant over the image. So they can't handle a situation where the optical properties of the water might change from pixel to pixel. And what you do is you get in a bunch of places where you know the depth, like these points. So you need actual data, and you can get that either by surveys, multi-beam echo surveys, or LiDAR sometimes. And then you make a regression, and you see both of these have got a log transform in them, and that's where they embody this idea of exponential attenuation of light. So you just make a regression against your known depths and the band values in those locations, and then you can process the whole image to make a bathymetry map like this. The important point is, you see on this scale here, it goes to 15 meters. This is Lizard Island in the Great Barrier Reef, by the way. It goes to 15 meters here, according to this. So it bottoms out at 15 meters, but this is deeper than 15 meters. No matter what you do with bathymetry estimation, with these methods or the other methods, which I'll talk about later, usually they tend to bottom out at a certain depth, which is not really their actual depth. They'll work well down to a certain depth, and then they'll just say everything's at some maximum depth, which it isn't. This should be deeper than 15 meters. It's just something to know. Some, like commercial providers of satellite drive bathymetry, will put a mask. They have techniques. I mean, there's lots of different ways you can do it to determine what the sort of maximum depth you can estimate is, and they'll mask out all of that because they don't want to give a product to their clients that has like false depths in it. So you'll just get an area where say we don't know what the depth is because it's too deep, and that's essentially what it is. That's what's happening. If you can't see the bottom, you can't estimate the depth because you've got no reference. All you know is, the best you can know is that it's deeper than a certain depth. It's deeper than the depth where you can't see the bottom anymore, essentially. So that's a limitation. And I would say with the very best images, say Sentinel-2 images, you can get down to 30 meters sometimes accurately, but that's the very best you can do. 20 meters is more normal, and 15 meters here is also kind of normal. Bottom classification. So here we go. This is another empirical type method. So years ago in the 1990s, when this kind of stuff was first being done, coral reef mapping and this kind of thing using satellites, we just use simple classifiers like k-means and so on. And again, you need data. So you need to have gone on the reef and have data points. Here's coral, here's sand, here's seagrass. And then you put them into the classifier, train it up, and then you process the whole image, and you can make maps like this, and you can see the kind of classes you can get: dense seagrass, medium seagrass, reef matrix. You can't really get down to coral You know, ideally you want to say this is coral, this is you know, the biotic types, but actually it tends to be more like habitat level. So you have kind of different zones on the reef, and you can kind of identify them. It's very difficult to get down to the actual individual biotic types, like coral and algae. That would be the dream if you could do that, but it's very difficult because spectrally they're very similar. So this is something that's useful for these empirical methods. It's this depth invariant indices concept, and it's just a transform of the image that makes it easier to classify the bottom type. And actually, it's kind of a rearrangement of the equation that I just showed you for the bathymetry, the Lysenga bathymetry method. And again, it involves a log transform. And all you do is you need to just identify some places where you think the bottom type is the same. So I would go here, there's some dots here, which you probably can't see. But you find some points where you say, okay, it's a sandy bottom, but it's at different depths. So you've got a series of points over sand at different depths, and then you put a point over deep water, because what you need as the inputs is the reflectance of the deep water and the ratio. It works out the ratio of the bands, log transformed ratio of the bands. And essentially what it's doing, you don't need to know any other information. It's extracting from the image a kind of, it will take two bands and transform them into another band like this, where the bottoms that are meant to be, that you've told it are the same, or where they have the same reflectance, look the same. So in other words, I'm making this more complicated than it sounds. I'm making it sound more complicated than it is. You've got here sand. So look at this. This is a deep water area, but it's sandy on the bottom. And over here, it's shallow, but it's sandy. But they look totally different in the original image. They're bright here and it's dark blue. After you do this transform, you combine bands 2 and 3 using this little equation, and you end up with something where you see where the sand is now, it's all a bright value. So it's all a large number. And over here, where it was a bit darker, the bottom reflectance was darker, it's now a different number. It's a dark number. So things, it takes away the effect of the depth effectively. It gives you a layer where the bottom reflectances are the same, they should be the same in that layer. The values should be the same. And then if you put that into a classifier, it tends to work better, of course, because you've made them look more similar. Doesn't work where you can't see the bottom, you just get noise. So this is something that was used quite a lot, especially when it still is used now. But back in the sort of late 90s, when all this stuff was, there was a lot of papers about coral reef mapping coming out for the first time. Depth invariant indices was a thing that was published and was very useful. But I start to think about this a little bit, and this is where I start thinking, and there's something here I wanted to mention. So for me, it's kind of interesting because you haven't really given it any information it didn't already know. You've taken two existing bands and you've done a kind of transform on them, and you've made a new band. And to do that, you've used some data points where it's sand and one where it's deep water, which you probably put into your classifier anyway. So you're not telling it anything it didn't already know. In a sense, you're not adding any information. So I kind of have this thing, well, why do I need to do this? What does it tell me about this classifier, this machine learning, whatever it is that I'm using to do this empirical assessment? And so one way to think about it is like this, in my mind. Imagine you have two different types. This is like a spectral space diagram. So you have band 1, you have band 2. You have two types, type A and type B. And they have certain reflectances in spectral space, just in these two bands. And you can imagine if you had 3 bands, they would be a 3-dimensional space. When you put this into a classification algorithm or any kind of machine learning, it's trying to find a way to separate those two types. Yeah. So the most simplest kind of classification algorithm would be something like a linear discriminant analysis, which is so simple, I don't think anybody's ever used it. But just to illustrate the point, you might have a classifier that tries to separate these points by putting a line between them. And then it can say, okay, anything on this side of the line in spectral space is one type, and anything's the other type on the other side is the other type. And then you apply that to the whole image and it works like that. And so if they were separated like this, it would be great because it's 100% separable. But if you imagine that they're distributed a bit differently like this, well, you can't insert a line now between them. There's some on one side of the line. No matter how you do it, you can't get a perfect classification from the training data, yeah, or from the actual data that's there. because it doesn't have this kind of linear separability. If you do a transform on that data, if you recognize that maybe there's a kind of curve in the spectral space around where the points are distributed, you can do a transform and sort of straighten them out. And then the classifier will be able to separate the two types. The same classifier that just using a linear separability could do it, whereas it couldn't do it with the original data. And that's kind of what's happening when you do this depth invariant indices thing. You're not really giving it any new information, but you're retransforming the data so that whatever classifier or machine learning thing that you put it into can more easily do what it does and separate them. So that's kind of very interesting to me, because it's kind of this idea that, like, well, you know, you're talking about a limit of the classification algorithm. Whatever algorithm's trying to do the separation, what you're doing is you're helping it by getting past an inherent limitation. You're not giving it any more information. You're just retransforming it in some way. Because then you could have a situation like this where they're actually not separable. So things, two bottom types that you want to separate might actually just look the same in the image, and no transform you can do would actually be able to separate them. So you have a fundamental inseparability, as it were. So it's just a way of thinking about these kind of machine learning and classification algorithms. So this example is super simple. In the 1990s, we were using super simple classifiers like k-means, this kind of stuff, clustering algorithms. Nowadays, you've got loads of things, support vector machines, neural networks, random forest, all this kind of stuff. And you can take your data and just throw it in and see what happens. But my sort of thinking is, well, if you're not giving it any new information, you know, you're kind of learning. If it can't do what you want it to do, or they're all performing at certain ways, you may be looking at the limitations of the actual classifier and the structure of the data. It's telling you something about the structure of the data and what the classifier can and can't handle. And for me, that's actually quite interesting. You know, if you try a bunch of different techniques and you hit a certain level of accuracy, so they can't get above 80% accuracy or something like that, then maybe that's your fundamental inseparability there. Maybe you're getting to the point where they just can't do any better because there is no way to do any better with the data that you've given them. Or maybe if one does better than another, it's because it's telling you something about the structure of the data. That particular method is able to deal with that shape of the data in spectral space better than the others. So that was just something I was thinking about, and I wanted to flag up. So, you know, to sort of give you something to think about when you're doing these kind of things. But actually, I was really pleased to see Jorge's introductory talk talking about he's working on explainable AI, because it's basically the same idea. It's like, if you use machine learning techniques, I think it's really useful if you're not just doing like try a bunch of techniques, one works better than the other. I find it much more interesting to think about why, what's going on, what's happening inside there, what does it tell you about the data, what does it tell you about the fundamental limitations. So I just put that in there as something to think about. But if machine learning goes that way, I think it's a really good thing. You know, I think if we can like start, rather than just treating it as a black box that either works or doesn't, start looking inside and learning something about the data. That's the way forward, I believe. For that stuff. Okay, so only 2 more slides on this kind of thing. This is another idea here which people use nowadays, which is image segmentation. So everything we've been talking about pretty much on the whole course so far is per pixel. We talk about doing inversion modeling and so on single pixels. But what you can do in these kind of contexts for bottom mapping is you can do an image segmentation where you group together pixels that have similar reflectances. And then you have shapes as well. So we tend to call these super pixels. You're grouping the pixels together. So this is, again, this lagoon area in Lizard Island. And these dark patches here are corals. And you see they come together as a little cluster here with a certain shape and size. And so you can put those into a classifier or a machine learning algorithm as well. So it's got extra information then. It's not only got the spectral reflectance, where you'd normally take the mean reflectance over the pixels in the cluster. It's got the size of the cluster, the shape of the cluster, the orientation of it, and all of that. So it's extra information to work on. And the very most advanced benthic mapping techniques will do that, and they bring in other information as well. So talking about things like environmental data, wave energy, wind energy, because this governs the way the environment is composed. You know, coral reefs depend on the wave energy they form. Like I showed you, those spur and groove zones, that's a function of the wave energy coming onto the reef. That's how they form that kind of morphology. So you can take an original image, you can put in the original data bands, you can put in a bathymetry layer, which you can either get from the image or maybe somewhere else. Bottom reflectance, I'll talk about how we can get that from the imagery in a minute. Environmental data, segment the image, put it all into a machine learning algorithm, and then do your classification from that. So then you can map to whatever habitat level you're interested in. And if you want to look at the papers by Chris Rolfsma, is the guy that does this kind of stuff to quite a high level. I would say that this is sort of the end point in some way, well, not the end point because we can go further probably, but this is where we're at now with these sort of empirical methods for benthic mapping. Any questions so far? Because I shall now change topic. Okay, yeah. Yeah. Yeah, well, okay, so I'm going to get on in a minute to talk about methods that can handle variation in the optical properties, but there is a limit. I mean, if you're talking about benthic mapping, you know, you have to be able to see the bottom, otherwise you can't do it. But the flip side is if you're interested in the optical properties of the water, it's good when you can't see the bottom. So it all depends on the objective. I mean, these methods will all work the same in principle, but they just don't work so well. So that's, you know, essentially. Yes, horizontal heterogeneity. So in the model inversion methods, you can handle that, and hopefully I'll get onto that in a minute. So, but those methods I was talking about now, no, they would tend to assume the optical properties of the water are the same everywhere over the image that you're analyzing. Okay, sun glint correction of high spatial resolution images is something that David's mentioned already a few times. I'm going to go a little bit more into detail in this because it's quite important in this area of work, shallow water stuff, because we're using high spatial resolution images typically. And so the difference is here. So this is a Meris image. And we talked before, you know, it depends on the solar view geometry. So this is looking across the swath. If you're looking over there and the sun's over there, you see the glint coming from the surface. But because the pixels are very large, a statistical model can describe that. Typically the Cox and Monk equations is what we're using. So you see this smooth increase of glint to the side here. When you've got high spatial resolution imagery, you still get that, but you also get individual per pixel variation, and you can typically see the shape of the waves like this. So it's a different type of problem, and we have to use different techniques to correct for it. Ideally, you would avoid it. Ideally, you don't have any glint at all, because as I'll show you, there are various problems about correcting for it. But you can't always avoid it. And part of the reason for that is because we're using high spatial resolution sensors, which aren't really designed, or it wasn't within their design remit to think about aquatic applications. They're typically intended for land. So for example, Sentinel-2 here, depends where you want to image. So it has a relatively wide swath, which is goes out to about 12 degrees, I think. So, you know, at the edges of the swath, you can have quite a lot of glint, but it depends on the time of the year because it depends on the sun elevation. So this is just a plot to show, for example, Lizard Island, which I showed before, which is the X. You know, at certain times of the year when the solar zenith angle is high, in the sun is high in the sky, you have glint, quite a lot of glint. I mean, all the images have some glint at that time of year. You have to go to other times of the year to get ones with minimal glint. But the thing about Sentinel-2 is it has an overlap in the swath. So certain places are imaged on the east and the west side of the swath. So you get twice as many images, which is nice. But in those cases, you either get extreme glint because you're basically looking at the glint, or you get nice glint-free images on the other side. So this is Heron Island, which is actually on the edge of a swath, on the edge of two swaths. This is imaged on one side of it, and this is imaged on the other. So it all depends on the image acquisition strategy and so on, and sometimes some places will have a lot of glint, other times, other places you can get images with relatively little glint, but you can't avoid it, is basically the take-home message there when you're using these kind of sensors. So we have a glint correction algorithm. So I'm going to talk about this a little bit. This algorithm is an old algorithm. I published a paper about it, and my paper is often cited, which is nice. But actually, there were people had been doing this for years by the time I already published my paper about it. In fact, I think the first time this idea I've seen was in the 1970s, but it was just like one sentence in a paper somewhere. They didn't really go into it. They just said, "Oh, you can do this." So it's lots of variants of this method about. Essentially, what you're doing is you're using the near infrared as an indicator for the glint. And then you can use that to correct the glint over the whole image. So what you do is, just in practical terms, you first of all assume that the near infrared coming from below the water surface is 0 everywhere, which is obviously invalid. I'll get to that in a minute. But typically it's a low value, or it's a constant. Actually, the assumption is that it's a constant value, but it's easiest to interpret that it's 0. So you start with an area, you take a deep water area like this, and what you're looking at is you're saying, okay, it's an area where if there wasn't glint there, I'd expect it to be homogeneous. I'd expect that area to look the same. So over deep water, if this glint wasn't here, all the pixels would have the same reflectance. That's what you're assuming. And what happens is you make a regression. So if you look at the pixels, individual pixel reflectances like this, first of all, you see that they just shift up and down. And that's essentially the glint spectrum being added and reduced depending on which pixel you're looking at. And what you're going to do is use the near infrared here as an indicator for the glint and then correct the whole spectrum for it. So you make a regression like this. You take the near infrared band and the band you want to correct. Over that area, you get all the pixels and you make a regression like this. So you get the slope. And then when you want to deglint the image, you go to every pixel. This is the value of the pixel to be deglinted, and you just pull it back to the minimum near infrared in this area. So the assumption is that the lowest near infrared signal that you see in that training area is the near infrared that you should get everywhere. It's the no glint near infrared. It has, there's the darkest one is the pixel with no glint at all. And you just pull all the other pixels back to that band by band. So you make this regression for each band and then do the correction. And it's just a simple equation like this. Once you've done the regression, DI is the slope that you get for that band. There's a bit of a question about whether you do it before or after the atmospheric correction. I'm going to get onto that in a minute. In some ways, it doesn't make that much difference. I always do it before the atmospheric correction, but there's some qualifiers on that. So we'll talk about it in a minute. So this is what it looks like when you do it. And it is kind of like magic. So this is before the deglint. And you see you have this image here. And okay, there's an island here. You can see it's probably sand here. There's some dark stuff over here, but you can't really see anything. And after you do the correction, suddenly it all clears up and you can see all these features here on the bottom. This is algae, it would be kind of like a microalgae in the sand. And you can see things like these are coral heads here, and you see how there's a little halo around them, a little bright halo around these dots. And that's because it's a grazing halo. So the fish like to hang out where the corals are, and then they go a certain distance from the coral, eating the algae in the sand. So wherever you get corals, you get these kind of halos. And you can see all sorts of other features there in the bottom reflectance, which before you could hardly see at all. So it works really nice in terms of cleaning up an image and enabling you to see what's on the bottom. The circular things are corals. The dark part is a coral. So it's sandy, and then you have a big coral head just sitting there. Yeah, and the light circle around it is where the algae has been grazed. So in the sand, you have like little algae, you know, little plants and stuff growing, and the coral head is there. And fish, which eat the algae, like to hang out on the coral head. That's where they feel comfortable. So they'll be there, and they'll go a certain distance out into the sand to eat the algae, and so you get a halo around it where the algae's been cleared by the fish. And actually, it's a remote sensing thing, because I think there's at least one paper where they said, oh, we can do fish surveys by looking at the size of these halos. We can say, okay, the halo's bigger, it's because the fish are bigger, or there's more fish there, this kind of thing. I didn't think it didn't go very far, this idea, but it was a good idea. So, right, so that's the good thing. You do this, and honestly, if you do this yourself, it's like magic. You do it, you see it image, you do the glint correction, you're like, oh, that looks really great and everything. And it is really useful for empirical methods. You know, if you put it into a classifier afterwards, because you cleaned it up, it's going to work a lot better. It's not going to see all that pixel to pixel variation. But there are some caveats, and this is one of the reasons why I talk about this, because I know people use this method a lot. The first thing is that the result is very noisy, or well, quite noisy, for various reasons. One is you're combining two bands when you do this. You're using the near infrared band to correct a visible band. You're combining the information from two bands, so you combine the noise from two bands as well. So the result is a bit noisy for that reason. And also because you're taking a big signal away from a small one. When you do the glint correction, the glint can be very bright, and you're subtracting that from the reflectance. Any sort of error in that, I mean, it's not perfect. You know, you then have that left on a relatively smaller signal. And also it requires exact band alignment. So the glint has to be the same in the two bands, the near infrared and the other band. They have to match exactly. And sometimes, because different sensors might image different bands at slightly different times, the waves might have moved very slightly, or they just don't have exact geometric alignment. So that can cause a problem as well. Yeah, and so I'll just make this point actually here while I remember, because it's on air. Because of that, sometimes spatial filtering can be a really good idea at some point in your processing chain, depending on what it is that you're doing. You might want to do a spatial filter whereby, for example, you take you make each pixel the average of the 9-pixel block that it's in. So you're applying a kind of smoothing filter, spatial smoothing filter over the whole image, because that will get rid of some of this kind of pixel to pixel noise that you might have left over. Sometimes people don't like it because they say, oh, well, I had an image at 2-meter resolution. I want my products to be at 2-meter resolution. I don't want to put a spatial filter on it. But the point is, and what I always tell people, like in my mind, just because the image that you've got is originally at 2-meter resolution doesn't mean that's the optimal resolution that you should process it at. It doesn't mean that the image information at 2 meters pixels can support what it is you want to do. It might be better to spatially smooth, drop the spatial resolution a little bit effectively in order to get a better product, or to be able to do something that you want to do more accurately. And spatial filtering tends always to improve the accuracy. If it's bathymetry and you do a spatial filter, you always get a better bathymetry result. It's just the way it is. Yeah. Yeah. Yeah, exactly. So you would have each pixel, you look at the 3x3 block of 9 pixels that it's in, and then you make it the average of that block, and you just do that over the whole image. But you can do it in different ways. Obviously, you can make it bigger, a bigger window, or you can make it a smooth window, not just necessarily that block. It can be some kind of a function, this kind of thing. Yeah. So another problem with this glint correction is that it can tend to overcorrect if there's any near infrared signal coming from below the water surface. And oftentimes there is in shallow waters. So this is an example where these are corals here along this edge. And corals are very bright in the near infrared, as are other photosynthetic benthos, such as seagrasses and so on. And so if they're really shallow, you actually get a near infrared signal coming from them. And when you do the deglint, you see it's overcorrected them. It's tried to subtract a glint spectrum where there is no glint, and it's made them basically black. If you're going to put that into a machine learning algorithm or classification, it might not be a problem because you don't need it to be radiometrically correct. But if you're going to use a model inversion algorithm where you want correct radiometry, that is going to be a problem. And the final problem, and David alluded to this, is essentially to do with the idea of, well, we've assumed that the darkest pixel in our training area didn't have any glint in it. But say you've got 10-meter pixels, within that pixel, you don't know what's going on. You've got a dark pixel, okay, you think there's no glint in it because it's the darkest one. But there might be a little bit of wavy stuff in there. There might be a bit of glint. You don't really know. And so the trouble is, what do you do? you might not have completely corrected the image, in which case it's going to be radiometrically off. But the real problem comes with when you have the interaction with the atmospheric correction, because as you saw from David's talk, near infrared is generally quite important in the atmospheric correction. You either use it directly to determine the aerosol optical thickness, or even if you're not using it directly, if you're doing a kind of spectral thing to try and do the atmospheric correction to determine the aerosols, the near infrared tends to be important because it's the place where you see the biggest effect. So you're trying to use the near infrared for two things. You're trying to use it to determine the aerosols, and you're trying to use it to do the glint correction. And there's a potential for confusion between the two. There might be some residual aerosol, there might be some residual glint, depending on which way around you do it. Which means, you know, radiometrically, is this glint correction really as good as it needs to be? It depends what you're doing. It might be, it might not be, but it's a kind of a problem with this stuff. There's two ways around the problem. The first one is the strategy used in this paper by Tristan Harmel, which is on glint correction and atmospheric correction of Sentinel-2. And essentially, they pull in ancillary data for the aerosol optical thickness from Aeronet station. So there's an uncertainty there between the aerosols and the glint. But if you can pull in ancillary information about the aerosol optical thickness, then you're adding information to the system to kind of help you resolve that uncertainty, which might enable you to do a better job. And the other strategy, which actually is more what I would tend to use, or what most people would use, is to recognize that we don't really need to separate the glint and the aerosol. We just want them both to go away. So actually, maybe it doesn't matter if you've got a little bit of residual glint that then goes into the aerosol optical thickness estimation, because the aerosol optical thickness, the spectral properties of the aerosol reflectance might be kind of similar to the glint anyway. So maybe they're just going to work together. There might be a bit of uncertainty in which is which, but overall, it might be reasonable. I mean, there's scope for more work on this. We just tend to assume that it's not a problem, but actually, you know, you could do modeling, you could do stuff to look into this in more detail. But I don't think I haven't seen anything recently on this. Okay, any questions on that? That's the end of the glint correction bit. I make a point of talking about this because the paper makes it seem like such a great method, and actually there are lots of caveats there, which I think people should be aware of. Yeah. If you have spatial variation in the water leaving near infrared, yeah, you'll have a problem. Exactly. So if you have some big plume of sediment, so when I did this, like what, for example, what you definitely don't do when you do the training here, what you definitely don't do is pick an area where there's a big plume of stuff going through it. You try and pick an area where you think it's homogeneous. But then if somewhere else there's a plume of something, it's not going to work there. It's going to cause a problem. If there's a near infrared signal coming from below the surface, yeah. You could do it, but the assumption you would be making is that the near infrared coming from below the water surface was the same everywhere. So it doesn't have to be zero, but it does have to be the same everywhere. Yeah. So yeah, you can use it, but because it's not a perfect. None of the thing is one of the main things about this stuff that's different, I guess, to your ocean color approaches is this is not per pixel. We tend not to do very many per pixel things with high spatial resolution imagery. Our atmospheric corrections will tend to assume the atmospheric properties are the same over the whole image. You will assess them somewhere and apply them over the whole image. You don't try and do per pixel atmospheric corrections because you can't, because every pixel is different in the shallow water area. It's got the bottom reflectance. And it's the same with the glint correction. It's something that kind of assumes that you can determine something in one part of the image and then apply it to the rest of the image. So, yeah. Well, that's the question, whether you do it before or after, because there's that uncertainty. You can do it, in theory, you can do it before or after, as long as you don't do a per pixel atmospheric correction. That's the thing. So I tend to do it before, because what you're doing is then pulling down to a minimum near infrared that still contains the aerosol optical thickness information. Yeah, because you've got your area, you train it, you say the darkest pixel is no glint, because you're looking at the pixel to pixel variation. So you assume the aerosols are the same. You pull down to the minimum near infrared, and that minimum near infrared is what you then go on to assess the optical thickness of the aerosols for the atmospheric correction. But again, it's not per pixel. You have to. We're talking about an image-wide correction. You know. After I've tried, so if you do it after, the problem then is where do you get your aerosol optical thickness information from for the atmospheric correction? So what you've got, so again, like it depends on the atmospheric correction algorithm. If you're using something like a dark pixel, something that relies on a dark pixel, that is then also going to look for a dark pixel. It's going to see that dark pixel. It's going to say, oh, okay, I'm going to get my aerosol optical thickness information from this dark pixel, but that near infrared signal may still have some glint in it. And this is the issue that I'm talking about. So you might have a combination of aerosol and glint in a pixel, and you try and correct for it. You might be putting that signal into another correction, as it were. But maybe it doesn't matter. Maybe it doesn't matter. In fact, what I would thinking about this is, well, when you do that regression, what is actually the shape of the glint reflectance? What does the glint reflectance look like? And actually, maybe it looks like something like the aerosol reflectance. It might do, you know what I mean? Because there may be some interaction with the aerosol. I don't know exactly the scattering, and you know, we tend to assume it's white, but we don't assume it's white. We actually look at the spectrum of that from the regression. So yeah, I don't know. Okay, anything else on that? No. Okay, so how are we doing for time? No, I did have an idea about this. Okay, so all right, we're doing all right. Right. Okay, so next topic, inversion methods. Well, you've heard about inversion methods already, so I'm going to talk about it in a shallow water context where bottom reflectance is a component. So these are the things that we're interested in. You might have suspended materials in the water column, phytoplankton, dissolved organic matter as well, and sediments. You've got the bottom here with the reflectance with different things on it. And you've, of course, got a variable depth. So what we want to be able to do is go from the remote sensing reflectance in a pixel in an image to get to quantify some of these things by model inversion. So the first thing we need is a forward model, a model that will enable us to model remote sensing reflectance based on the input parameters of depth, optical properties of the water, and bottom reflectance. So one model we've seen already that can do that is hydrolite. You can put in a bottom reflectance, optical properties, depth, run it, and get a reflectance, remote sensing reflectance. It's relatively slow to do it each time. So what we would tend to do is build lookup tables. We'd run it over and over again, different bottom reflectances, different depths, different optical properties, and build a big lookup table of reflectances, which we can then use for inversion. Another approach is the semi-analytical models like Zongping Li's work. And in fact, I'm going to show in a minute, he has a semi-analytical model for shallow water reflectance. And the idea of that is it's a set of simpler equations that approximate the same function as hydrolite, not quite the same, but what you tend to do is you have a basic principles like your reflectance is, what is it, BB over A plus BB, this kind of thing. And then you can use hydrolite to build regressions for some of the coefficients. So you might run hydrolite over and over again to get some idea about what some of the numbers in those equations ought to be. You build an equation and it gives you at the end a set of equations that quickly can give you remote sensing reflectance from those input parameters. And then you don't necessarily need to use lookup tables because you can use that equation directly in the inversion. I'll show that in a minute. So the first simplest thing is spectral matching. So you could use hydrolite, like I said, to build lookup tables. And then what you do, you've got a pixel in your image. You go, oh, I wonder what this is. And you go through your lookup table, which has got all the different depths tabulated and phytoplankton, CDOM, other properties, whatever you've characterized. And you find the spectrum that matches best the spectrum in the pixel. This is after you've done your atmospheric correction, obviously. And then when you find the spectrum that matches the best, you know, say it's this one, You say, oh, okay, the depth is 2 meters, there's 0.2 milligrams per cubic meter phytoplankton, there's so much seed on, whatever is in that table row. And so you're getting everything all at the same time. You get the depth, you get the optical properties, you get the bottom reflectance. And an important point that I mentioned before is that you want to convolve these hyperspectral profiles to the bands to do this accurately, because the bands are wide. So you model hyperspectrally, and then you use the spectral response function to convolve to the bands to find the best match. And for spectral matching, you usually use an algorithm like there's different ones, but the most common one is Euclidean distance, where you just take the square of the difference in each band and add it up. So you're looking to minimize that number, find the spectrum that matches the best. So this is a semi-analytical model, Zongping Li's model here. A lot of people have used this. This is a really popular model. I think pretty much everybody uses it for doing bathymetry, satellite-derived bathymetry, by these model inversion methods anyway. It's an alternative to an empirical method. Looks really horrible, yeah, but it's not that bad at all. First of all, this is the output, remote sensing reflectance. This is subsurface remote sensing reflectance. So you have another little transform that you do to take that to big RRS, above surface, just a simple equation. So that's your output. These are inputs. P, G, and X are phytoplankton concentration. It's a proxy for the phytoplankton concentration. It's not actually in the right units, but it has that meaning. Dissolved organic matter is G and backscatter is X. So that's just 3 numbers, yeah. The other input here is H, which is the depth. And then finally, you've got the bottom reflectance. The spectral bottom reflectance is an input to these equations. But everything else is known. The equations just follow one on from another. So these are the only inputs. So basically, you've got a model for remote sensing reflectance based on the phytoplankton, the dissolved organic matter, the backscatter, the depth, spectral bottom reflectance, and wavelengths. So wavelength spectral model. And so that's just 4 numbers and a spectra, basically. And it's quick to evaluate. It's a bunch of equations, but they're very quick. Just calculate in a piece of software. So you can use that you can use that in a successive approximation algorithm. So that will be an algorithm that's going to start with a guess, see what the remote sensing reflectance is, tweak the numbers a little bit, compare it to the remote sensing reflectance you want to get from the image, and just keep adjusting it until it finds a match. So no lookup tables, you just use the equation directly and adjust the parameters. A bit like you were doing yesterday with your spreadsheet, but you have an algorithm to do that. Bottom reflectance can be handled in different ways, but one common way is to have a spectral mixing model, what's called a linear spectral mixing model. So I showed at the start in the slide about how you can have sand and corals, and then at a certain resolution they kind of occur together in a pixel, so you can't really separate them. So you have a model like this where you have a sand reflectance and a coral reflectance, and you just mix them together based on the proportion. So if you thought it was 20% sand, it would be 0.2 times the sand reflectance plus 0.8 times the coral reflectance, and that would give you your bottom reflectance. So that's a way to handle variability in the bottom reflectance. Usually you have a spectral library of maybe, I use like 6 different reflectances, and you can have any pair of them and you can mix them. So you end up with a model for bottom reflectance that is basically has one number, which is which pair have you got. So if you've got 6 different possible bottom types, you can make a pair like 15 different ways. And then another number, which is how you mix that pair together. So it simplifies it down. So you end up with a model like this, which is just 6 numbers for each pixel. And this is what you use in your Levenberg. Well, one of the techniques is called Levenberg Marquardt. It's a successive approximation technique that's going to take that, adjust the numbers until it finds a spectral match. And you do that for every pixel. I'll just mention one thing, because you often see it said sometimes. People will say, oh, well, there's 6 unknowns here, PG, X, H, M, and E. I've only got a 4-band image, so I can't use it because I've got more unknowns than I've got bands. You know, it's like this kind of linear algebra concept that you have to have as many equations as you have unknowns to resolve it. But it doesn't mean you can't do it. You can still do it. The only problem you would get, or the main problem you might get from having too many parameters, is that there's too many different solutions. So you might be able to get a good spectral fit with different values of your parameters. Maybe the depth is higher and the bottom reflectance is so you've got it's deeper with a brighter bottom reflectance would be the same as shallower with a darker bottom reflectance. There might be some confusion there, but you can still apply it. It doesn't stop you applying the method. And the other thing to bear in mind, which people often don't realize when they say this, oh, you can't do it, too many unknowns, is that these are constrained values. So P, G, and X, which are concentrations effectively, can't be less than 0. And normally you would put in a maximum value as well. You would say, oh, okay, I don't think the phytoplankton can be of a higher. I mean, you know something about the area. You say, oh, this is the maximum I expect phytoplankton to be, and so on. So these have upper limits as well. M is already, that's the mixing parameter, so it's already constrained to be between 0 and 1, and E is just an integer number from 1 to 15, like I said, to select which bottom pair. So it's a constrained system. So that does mean actually it's more solvable than you might think, even though you've got 6 unknowns and you might only have 4 bands. And this is an example of the kind of outputs you get. So for every pixel is processed independently now. So unlike those empirical methods that required the assumption of the optical properties of the water to be the same everywhere, this doesn't. It's matching to every pixel and trying to estimate the depth, the optical properties of the water, and the bottom reflectance. So again, it's the same site which I always use for my slides, Lizard Island on the GBR. Yeah, it's good. Yeah, it's good, isn't it? Have you? Well, yeah, we'll talk about it later. But yeah, it's good. It's great for these kind of slides. So yeah, here it is. Again, same spot. This sort of lagoon here. This is the original image. This is the bathymetry map coming out of this inversion method, and you can see it looks kind of reasonable. Deep water here, 15 meters, and then even deeper over here where it is deep. This is the bottom reflectance. Kind of looks reasonable. It's got that thing I talked about, like this is sand here in the original image. It looks deep here, blue, dark blue, and over here it's bright. But in the bottom reflectance, reassuringly, the reflectances are similar. And over here you see this orangey color. That's where there's corals. There's corals here. So the bottom reflectance kind of looks reasonable. Now the water optical properties, here we have a slight problem, and this is the important thing to point out. So this is, I've converted it into KD par just to make it something tangible. And you can see, okay, well, I see all these features here in the water column optical properties. Well, they're not real, obviously. This is not real. This is picking up something from the bottom reflectance and putting it into the water optical properties estimation. And the reason is, of course, because these areas are very shallow. So you've got a very short path length through the water, and the water is fairly clear as well. So it's going to have great difficulty to estimate anything about the water optical properties with any accuracy in shallow areas where, you know, there's not much signal for that component. So it kind of falls apart there. But if you look in the deeper areas, it's kind of homogeneous over this area and out here in the deeper area. And the value of 0.2, it's not validated, but that's a reasonable number for this kind of environment, I think. So it can work where there's enough signal. Yeah. Mm. Mm. Yeah, you would, if the KD is high, you wouldn't be able to do the bottom mapping. So what would tend to happen is this one would get a lot worse, but this one probably would get better because you'd have a better signal from the water column. So you'd be able to estimate your water column properties better, but that would be at the cost of the bottom reflectance and the bathymetry as well. You would have a harder job to do the bathymetry. Or certainly you'd maybe only be able to do the bathymetry in maybe the first 5 meters or something like that. So yeah, they sort of trade off against each other in that way. Okay, so any questions on that? Because I will move on slightly. to canopy modeling. Okay, canopy modeling. So I've talked about bottom reflectance, like you can just stick in a bottom reflectance of sand or a bottom reflectance of coral, but actually what's on the bottom is already optically complex. So let's say seagrass, is it just a green spectrum? Well, no, not necessarily. So for an example here, we've got a sparse seagrass canopy and a dense canopy, and you can see just by looking at it, you know, it's got shadows inside it. This sparse one, you can see the sand between the blades. You know, it's complex optically already just in that bottom. What's on the bottom is optically complex. So you know, should we just plug in a single reflectance? Well, we can perhaps think about something more complicated, and one way to do that is to talk about canopy modeling, and that's a generic term. So this is a vegetative canopy, but you can also talk about canopy modeling for coral reefs. You know, the coral reef has a structure as well. So there's not so many people doing canopy modeling in aquatic applications, but it's more common in terrestrial remote sensing. So you get forest canopy models, this kind of stuff, quite a lot of papers on that kind of thing. It's something that I've worked on a little bit over the years. So here I'm just going to show, to give an idea of what you could do, this seagrass canopy model that I've worked on. I think in 2010 was the first time I published anything with, I was working with Susana Enriquez, who's a seagrass photobiologist based at the National University of Mexico. And we developed this model, and I've done some applied work with it with Heidi Deers and her group as well. There's a couple of papers about it. So the basic idea is it's a geometrical optics model that you can put a physical canopy structure into, and then you can, in the model, irradiate it with light from above and look at the reflected light and get a reflectance based on the structure of the canopy. So then you can vary that structure of the canopy to understand the variation in the reflectance that you would get as a consequence of the fact that these environments are not necessarily that simple, and you know, the leaves can take different positions and this kind of stuff. The model itself it's not a Monte Carlo model, it's a different type of model, but you could use a Monte Carlo model to do this kind of thing. This is how it's set up. Each leaf is just a simple, I mean, this is fortunate about Thalassia, the species we're modeling. It's just a very simple straight leaf. So we model the leaf as a series of polygons like this, and onto the leaf polygons we map the reflectance and the transmittance of the leaf. So this is the kind of stuff that Susanna's measured in the lab. You know, it's a lab measurement. You take the leaf, you put it into your equipment, and you measure the reflectance at the scale of the leaf surface. And the leaves transmit as well. They're not opaque, so some light goes through. So we map those properties onto the surface of the leaves, and we have at the bottom a sand reflectance for the substrate. So we put the sand reflectance there. And then we can build a physical model of the canopy, and it's kind of a physics thing where the leaves are kind of flexible. They're like springs and particles, so they can bend. And then I put a force into the model based on a wave motion. So the idea is that these leaves, which might just be standing upright, get pushed backwards and forwards by the wave energy, and we'll assume naturalistic positions. Yeah, that's the idea. It's not, we can't validate it. We can't really, that's very hard to look at an actual canopy. So the idea is just to get a range of the physical state of the canopy, so we can look at the variation and reflectance over that sort of realistic range of variations. So I can animate that. So this is actually from the physical model that puts the wave energy in, and it pushes the leaves backwards and forwards. And for any particular position, I can take a snapshot and model that in the model to look at the reflectance above. So these are the actual outputs of the model, but looking from the side. So we actually look from above to deduce the reflectance. So this is for, so I didn't mention leaf area index. LAI is a measure of the density of the canopy. So LAI is the area of the leaves divided by the area of substrate that they're on. So an LAI of 4.5 is quite a dense canopy, whereas an LAI of 1 is a relatively sparse canopy. So I can also animate this. So it's the actual model output, but viewed from the side. And you can see some of the optical processes that are captured, in particular the sand here gets brighter as the leaves come to a more upright position. And that would be the case that if you looked from above, when the leaves are relatively upright, you can see into the canopy more and you see more of the sand, and it's probably a brighter reflectance. And as the leaves come over, you don't see the sand anymore, so the reflectance will go down. So the idea was to try and capture some of these processes. And of course, there's all sorts of interactions between the individual leaves. The light propagates through them. Some of it transmits through and reflects back. So you've got multiple scattering in the canopies and so on. So I put this into a multi-factor model where basically leaf area index is what we want to be able to estimate from the imagery. That's what we're interested in. Canopy density measured as leaf area index. So it's a 3-factor model where the leaf area index is varied, but also the canopy position is varied by this thing I just showed, and the leaf lengths, because you can have the same density of canopy, but with more shorter leaves or less longer leaves. So that's another canopy structure variation. And you just model them over and over again, and you view from above, you get the reflectance out, and then you have to skip the details. Basically, it's like a semi-analytical model. Just reduce all this model down into a simple equation that gives us the spectral reflectance of a canopy as a function of leaf area index and a parameter E, which varies from 0 to 1, and is just the first order variation in reflectance. That captures the fact that the reflectance can get brighter and darker, and other interactions, multiple scattering interactions, lead to variation in the reflectance. And you just condense that down into a single parameter to express the first order of that variation. It's just a lot of regressions and stuff. I'm going to show the details. It's in the paper. But basically now what we've got is a model for bottom reflectance, a 2-parameter model for spectral bottom reflectance, which is leaf area index, which is what we want to know, and some other parameter that just encompasses the variation. So we can then plug that in to Lee's model for shallow water reflectance as our bottom reflectance model. So we get rid of that spectral mixing thing, plug this in, and now you've got a model for estimating leaf area index of seagrasses. But it only works where you only have seagrass and sand. It doesn't work for corals anymore. There's no coral reflectance in it. You can only apply it to places where you've only got a variation of sand and seagrass. So this is what it looks like when you run it. And this is Yucatan in Mexico. It's south of Cancun. It's the Puerto Morales Reef Lagoon, which is a marine protected area. Along the edge here, you've got corals. This is the coral reef. And inside you've got a lagoon, and this is all seagrass and sand. Basically, we know there's a few other bits and pieces in there, other benthic types, but it's dominated by this species of seagrass. So it's kind of valid to apply the model. We cut it off where the corals are because it can't do that. And so we have an estimation here of leaf area index per pixel done with this inversion method. And you see it kind of looks reasonable. You know, it's a high leaf area index where the canopy is dense. Is it good? Did you have to validate it? Obviously, we have to go. Now, for this study, there was leaf area index data available, but it was collected before the remote sensing was even conceived of. So this is data that was collected for ecological monitoring purposes, not for remote sensing purposes. And it's actually a common problem in getting good benthic data at the kind of scales you need to do validation of remote sensing products like this. And now this is a good illustration of one of the problems you have. I mean, overall, it's not too bad. We don't have that many data points, but they're okay on the one-to-one line. This is the field data, leaf area index, and this is the estimated from the image. There's the one-to-one line. They're not too bad. We have error bars on them, so within the error bars, they're pretty close. But then you have these outliers down here, and you think, oh, what's going on there? That's the field data says it should be a very high leaf area index, but the estimated one from the image is very low. But then when you look very carefully where these points are, and there's just one of them here, but it's true for both of them, they're really close to a high leaf area index area. They're literally 5 meters out, because these are 10-meter pixels. It's Sentinel-2, yeah, we're using here. And so actually my interpretation of those is, well, that point is actually here. It should be in this dense seagrass area. It's a very thin seagrass area close to the coast here. You see it here. And we're just off with our geolocation accuracy for whatever reason. I mean, the first thing is, you know, when you're doing these surveys, you're underwater and your GPS doesn't work underwater. So to know exactly where you are is not so easy. You know, the imagery, probably geolocation could be added a little bit as well. Half a pixel, that's probably within what you would expect for Sentinel-2 anyway. I don't know what the latest on that is. I know they improved it at one certain moment. But, you know, so this is the problem that, and it's a general problem for benthic mapping, is that getting data for validation at the appropriate scales for remote sensing is very hard. There's very different types of data. The data you can get at remote sensing scales with 10-meter pixels. I mean, a 10 meters by 10 meters is big, yeah. And then you're down there looking at it. Well, how do you know what the leaf area index is at that scale to register accurately with an image? It's very, very difficult. So that's just a general point there to think about. But overall, it kind of works all right. So any questions on that? Because I shall now move on to uncertainties, such like. Right, now I've got time to do this. Let me say I start going, oh yeah, maybe I'm all right. I might be on time. Okay, so related to what I just talked about, what about uncertainties? What about confidence in our estimations in benthic mapping, or also applies to bathymetry? Say, for example, you had two images of canopy density, like I just showed. You analyze one image, you analyze another, you look at them, they seem different. In one place, the canopy's got less dense, or whatever. Has it really, or is it just down to the uncertainties? How can we come to understand and be confident in our conclusions about differences between different images that we've analyzed or changes over time? And there's two possible approaches, which I'm going to mention, briefly talk about. And one is, in the model inversion methods, it's possible to do a uncertainty propagation through the inversion. And the second one is using multiple images, what we can do if we use multiple images. So first one, uncertainty propagation. Well, I've mentioned this before, this concept of fundamental uncertainty. If all you've got to do your analysis is the pixels in the image, then if two pixels look the same, if they can have the same reflectance, you can't distinguish them. So here's an example: sand at 20 meters reflectance compared to coral at 4 meters. And the reflectances are kind of similar. So, but they're not exactly similar. So the question is, how similar is too similar? If they were exactly numerically identical, you definitely could not distinguish between them. You could not accurately say that something was sand at 20 meters or coral at 4 meters, because numerically their reflectance would be the same. You'd be totally lost. But of course, they're not going to be numerically the same. They will have a little difference. The question is if that difference is detectable. So one way we can have a look at this is to use an image-based noise model and propagate it through the inversion. And what we would do typically is look at an area of the image where we think, again, deep water area, where we would expect it to have the same reflectance in every pixel if it wasn't for some kind of noise process. And when you do that, typically they look like this. You'll have, it's like I showed with the glint. And in fact, that is probably the main source of variation here. You've got a certain spectrum, but it kind of shifts up and down a little bit like that. And it's, again, it's this concept of within the pixel, you don't quite know what's going on. Little surface undulations, they're tilting a little bit towards and away from the sun. So the reflectance is going up and down. And there are other sources of noise as well. The instrument itself will have a certain amount of noise, instrumental noise. And we just lump all of that together, take a part of the image where we expect the reflectances to be the same, and then we can build a noise model from that. And basically, yeah, just to reiterate what I said, we're taking everything from the subsurface, including the surface reflectances, the atmosphere and the sensor, and just lumping it together in some kind of model for the noise based on a sort of sample area in the image. And the important thing is it needs to be a spectrally correlated noise model. Some people do this and they just look at the standard deviation in each band, but the point is the spectra tend to shift up and down like this. So you will tend to overestimate the noise if you look at the bands independently. You really want to use a spectrally correlated noise model. So you've built this noise model, which basically means you just have an equation with some parameter that gives you different kind of variation in the reflectances. It's like a noise term that you can add on, randomly generated. So now instead of inverting each pixel just once in the inversion model, you say invert it 20 times. And what you do each time is add on a noise term from your noise model. So you're perturbing the reflectance you've got in your image by the model of the noise that you've generated from the image. And when you do each inversion, you then get slightly different estimates. You'll get a slightly different estimate for the depth, slightly different estimate for the optical properties of the water, for every parameter. You do it 20 times, 20 estimates of the depth, 20 estimates of each of them. You can then have a confidence interval. So typically you would take the mean value, and then you could, for example, take the 90% confidence intervals. And the funny thing is when you do this, you actually get a better result anyway. The mean value that you get when you do this noise perturbed multiple inversion thing where you then take the average is generally a better result than if you just did it once, for reasons I don't fully understand, but it's to do with sort of exploring the space of the possible solutions. You know, it just generally comes out as when you do your regressions against bathymetry data, generally comes out better. So anyway, it's a method of giving you confidence intervals on every parameter. And just to give an example of how it works or what it looks like, this is applied to two sets of data. Again, it's a coral reef area. This is Cassie, is an airborne hyperspectral imager. So it flies low, it has relatively good characteristics, and it's got many bands. And QuickBird is like, I don't even know, I mean, it's not up there anymore, I don't suppose, but it's old data. It's a high spatial resolution, one of these commercial type satellites. I think it was 4 bands, maybe 4 meter pixels, something like that. And this is estimation of the bathymetry using model inversion method with the uncertainty propagation. And you see across, it's along this line here. So this is a reef flat, and then it goes a bit deep, and then you've got a coral head here, and then another coral, and then it's going deeper over here with a sandy bottom. And you see with the Cassie, it kind of shows that estimation of the depth going down here, quite reasonable. And the gray area is the 90% confidence intervals. So they're quite narrow. Most of the depth estimates from that noise perturbed inversion are coming out very similar. With the QuickBird, it's similar in the shallow areas, but then as you go deeper, it kind of goes wrong. It's that thing I showed before about it bottoming out at a certain depth. It thinks the depth is maximum about 4 meters, which it isn't. And we can see in the image it's going deeper than that. But it is reflected, that error is reflected in the uncertainty, the confidence intervals here, because you see the confidence intervals are starting to get big. So what it means is we kind of know there's a problem here. We know that this could be inaccurate. If we didn't have this analysis, we just had this one, we could say, well, okay, we think we're getting the depth down to here, okay, but after here, we're not sure. It could be deeper, or it could be even a bit shallower. We're not really sure what the depth is there. So it's a way of propagating uncertainty through the inversion algorithm to give you some kind of confidence in the estimates. And for satellite-derived bathymetry, for hydrographic purposes, this is really important stuff because they really want to know the uncertainties. That's key to them, is to have some estimate of the uncertainties. Any questions on that? Yeah. Yeah, okay. So I tend to use mean sea level. So it depends who you work with. Some people, yeah, so Lachlan's question is about tide corrections, which I've totally skipped over. But yes, if you're doing, especially if you're doing multiple image analyses, you need to do tide corrections. If you're in a place where there is a tide, and in some places there's not much tide, you can get away with it. But yeah, so and then you'd have a datum which is you have to correct to a certain datum, which could either be mean sea level or lowest astronomical tide. So hydrographic offices tend to like to use lowest astronomical tide. So you're pulling all the images to that sort of depth, or others would be in more environmental kind of applications. I'm generally using sea levels. So. Okay, so multi-image analysis. Right, we have a lot of images these days, many images. Sentinel-2, for example, most of my examples are from Sentinel-2, is a 5-day revisit. Some places it's even better, depends where it is. So you get an image every 5 days. In 1 year, that's a lot of images. The question is how best to utilize this archive of images. Say we want to do some sort of benthic mapping or bathymetry mapping exercise. I'm talking about things that don't necessarily change over time. So maybe not so appropriate for optical properties of the water, but if you wanted to do something where, you know, you've got a time range, it's not critical what time point you use the image from. What do? Well, the simplest thing is you look at the archive of images and you pick a good image. You just look through. Some of them have got some clouds, some of them look a bit hazy, you don't like the look of them. You pick a good one and you make your product from that good image. Well, that's cool. I mean, you've used the archive in some sense because you've looked through it and you found a good image. So it's good that you had all those images to look through. Another method, which is becoming quite popular, I see quite a few examples of this, especially using Google Earth Engine and this kind of thing, is to make a median image. And in that case, you go through all the images and you align up all the pixels. And for each pixel, you make it maybe the median or some other statistical derivation. It could be a percentile, a certain percentile of the image, of the value of that pixel in all the images. So in each band, you might take the median over all the images, or you might take, as I say, like maybe a low percentile to throw out the outliers, to throw out cloud. Cloud pixels are bright, values are bright. So if you take a median or a low percentile, all the cloud disappears. And you end up with an image like this, which is quite nice. It's nice and clear, and it's in some way using the data from all of the images that you input to it. You can actually see here a little bit of glint on this side. So it can't get rid of everything because these images will tend to have glint at this particular site on this eastern side. So it actually kind of pulls that out a little bit. But for this area, it's nice and clear. And you can then use that to make your product. But I feel a little sort of uneasy about an image like this because I'm not really sure what it is anymore. It combines pixels or data from a whole series of images, and sort of radiometrically, what actually is it now? You know, I mean, like we just talked about, the tide varies from image to image. So you've got some kind of weird conglomeration of these original raw data. You know, so if you're going to do a physics-based inversion type method, you're kind of like, yeah, what is it exactly? And what, you know, I feel a little uneasy about it. Another alternative approach is to process every image to a product first and then take the median value to make your final product. So you process all the images through your processing chain for whatever it is you want to do, and then take the median at the end. Now, you wouldn't normally just throw every image in without thinking about it. You might screen some images that just look terrible and just, I'm not even going to use those. And you would also have a cloud screening step in your processing chain to try and throw away the worst data. But at the end of the day, what you've got is a whole series of products. Like, so for example, this is again, this canopy leaf area index. Process every image for leaf area index and then make a median product from the individual products, rather than starting by making a median image and then processing that. So it's heavy on the processing. You have to process all the images. The advantage of doing it this way is not only do you have the median of the product, you also have all the individual products. So for every pixel in your final output, you've got, okay, here's the median, but you've got that pixel processed in all the other images as well. So you have a probability distribution for, in this case, the leaf area index or the bathymetry. You don't just have one value. If you have a probability distribution, you can do statistical testing. So for example, this previous one, it's a good site, so I had a lot of images. So this is annual median leaf area index. So it's for 1 year, all the images for 1 year, 65 images in total, turned into a single product. Well, they're all processed, and then eventually you get a single product. But across each pixel, you've got the probability distribution for that year. And if you do it for separate years, as I've done here, you can then do a statistical test for changes in the canopy. So this is showing it's Mood's median test. So you're testing whether the median is different each pixel, and it's with a 1% probability. So I'm showing here where you've got a canopy increase or decrease with a probability according to the statistical test of better than 1%. So, and it's between 2017 and 2020. So I've got those two maps for those 2 years, and you can then do this statistical test because each pixel has a probability distribution. It's not the case that you're doing, and there's a lot of papers that do this, and we should, I think, move beyond this, where somebody will take one image and process it and another image and process it and say, oh, look, there's a change here. How do you know? You need to put it in the context of statistical confidence. And with all of these images, you can do that now, or at least there's methods to do that. And just finally, what does it actually look like if you look at one spot on the image? So this is just looking at a pixel at this yellow dot over the years. So it's been processed each year, but these are all the individual results. And you can see that the leaf area index estimate at this dot changes wildly for every image to image. But the line here, the step line, is the median from taking the median of the product. And you can see here, when you look at it, you can see with your eye, okay, it's gone up here. There's been a tendency up here and a tendency down, but the actual noise image to image is massive. So if you just took 2 images, if you took an image, here, that would be quite high, and then you took an image here, it would be lower. And you would say, oh, well, maybe it's got a bit less. But actually the trend is it's got higher over this time. So that's the importance of doing the statistical test. It actually tells you whether that, what you can see here with your eye, is statistically sound. Is that really an actual increase given the amount of noise? And at this spot it is, because it comes out as higher than, more significant at the 1% level. So that's something that I think we can do now with all these images. It's for things that don't change over time, where it's okay to take a bunch of images and say, okay, in this period we think it's the same, and then we just jump ahead in time and group together images that way. So it's useful for benthic mapping and bathymetry and stuff. Any questions on that? I've only got one more sort of thing to say now, right near the end. Okay, carry on. Yeah. Yeah. Yes. Well, you can't. That's the point, isn't it? You can't. That's why you have to my mind, it's better. I mean, no, it's better, but it's hard work. You have to process every image and then take then you've got the uncertainty, the data for the uncertainty estimate at the end. And that's kind of what I'm advocating here, because you can do it. I mean, it's just a proof of concept, really, in a way. There's a lot of work to do to see still whether it's valid and this kind of things. But you can do it. There's a way to approach it, at least. Yeah. I've never seen it. I've not actually seen it used anywhere. I mean, I haven't seen any. I'm not saying it hasn't been done. I mean, I don't always read all the papers that come out and stuff, so I could be missing something. But I've never seen this actually done in this context before, so I don't know. Okay, well, I've just got time, because actually I'm on time now, so I've only got 3 more slides, and I just want to mention it because we've been talking about it a little bit. Spaceborne LiDAR, we were exciting possibilities for ocean color, but actually those exciting possibilities are already here for shallow water mapping. If you're interested in the bathymetry, or if the bathymetry is of useful data to you, because we've got ISAT-2, which was launched in 2018. It's a spaceborne LiDAR. It's an altimeter, so it's intended to see the height of the land. But it's great because you can see into the water with it a little bit. Not great, but enough to be useful. Being LiDAR, it's like I think David pointed out, it's track data, so you don't get an image, and this is the kind of data distribution you get And again, it's this same area. This is the lagoon I was showing before, the Puerto Morales lagoon. This is Cancun here. So you get data in lines like this across your scene, but you know, in a good spot, you can, well, it's global. The acquisition is global, so you can kind of get this pretty much everywhere. So you can extract data in transects across your site of interest. And this is kind of what it looks like. This is a side view, essentially. So we have the height of the returns. Each dot is a single photon return. This instrument can measure individual photons. It shines a green laser down. There's 3 of them, well, actually 6 in 2 pairs, 3 pairs, as it were. It counts the individual photons that come back, and it gives you an estimate of the height based on how long it took for the photons to come back. And so what we're looking at here, this is the sea surface. It's like a side profile. You imagine we're looking at a slice from the side like this. This is the sea surface. So you get a lot of returns from the sea surface. This is the land here. And this is the bottom of the water. This is the return from the bottom of the water column. So you can see you can infer the depth from this between the water surface and the bottom here. You have to do like tide corrections and things like this to make sure you know, obviously you're going to a certain data like Lachlan was just talking about. But it means you can get the bathymetry and you can get estimates of bathymetry anywhere without actually going there. You don't have to go there anymore, which is really useful. And you can use these estimates of bathymetry for, if you want to do an empirical algorithm, you can use them as training data, or if you're doing model inversion algorithms, which don't need training data, you can use them for validation, which is what I tend to do. The only downside of it is very noisy, and you don't, this is what a good one kind of looks like. A bad one, well, you just throw it away immediately. I mean, there's so many of these tracks, like, I mean, I've processed maybe 400 of these manually for this big analysis we did. And, you know, you open up the image, you have to extract the data. It's kind of a pain. There's not an easy way to do it. You have to write a script and stuff. And you just look at it, it's just a massive point. So you just like, forget that, move on to the next one. But on a good one, it's kind of like this. You'll see, I mean, it's weird. I mean, this LiDAR stuff, I mean, there's returns here that supposedly from below the bottom of the water column, which they obviously can't be. I don't know what gives rise to that. Maybe it's a multiple scattering thing. Maybe the photons get kind of a bit lost before they come back again. I don't know. But you can see the bottom here kind of clearly. And as you go deeper, it gets more and more indistinct. And the problem with this stuff is I have yet to find a good automated algorithm to process it that works as well as what you can do by eye. Because when I look at this, I see, okay, here's the bottom. And I see it going here and I'm going, yeah, this is still the bottom here. But actually, if you just looked at this area in isolation, you wouldn't know that that was the bottom. It's only because it's a kind of continuation of this line. And that's kind of what like the data tends to look like. And if you process it manually, I mean, basically, I just clean these images up manually, take out the points, and then have a little script that will find the depth from the points that are left. So you have to clean them manually. So it's kind of laborious to work with. But in the best conditions, you can see depths of up to 20 meters, and that's in clear waters, obviously. So it's a really great data source, and it is actually kind of changing the way we do things a little bit with this kind of shallow water mapping, because we never had anything like this before. Yeah, and then this is just the final slide that shows, yeah, okay, the point of that's good about this kind of data as well is that the scale is appropriate to remote sensing scales. The footprint of the laser is about 10 meters on the surface. So it's very similar to Sentinel-2, and you can get data over very, very large spatial scales. So in this big analysis we did, it was 400 kilometers of the coast. I processed all the ISAT data that was available at that time. It's a few years ago now. It'll be loads more now, along this entire coastline. So I can do from the inversion, which was over 5 Sentinel-2 tiles. I've got a bathymetry map for this whole area, and I can validate it against the ISAT data across the entire coast. Whereas in the past, you might have had a few multi-beam scans here and there dotted around, but actually you can do your validation at the same scale as the remote sensing, which is really good. And yeah, it kind of looks reasonable. So that's a good thing. So that's the end. And if you have any questions, now is the time for them. Thank you very much.